Okay, for people joining this live stream, we are talking about dealing array management, array handling in Wolfram language. And to summarize where we were at last time, as I understand it, the first thing is templated array structures, the ability to have some way to describe how to access what a given element. There is a raw version of what the array is like, which is basically just some kind of array of whatever elements they are. And then there is a templating that allows you to basically say, the elements here represent, column name such and such and so on. Is that the way that we were describing it? Do you understand what I'm saying? We're describing. Can somebody speak up about this? Okay. Does anybody remember what we were talking about last time?
I think we were talking about a lot of different things.
Okay, well, let's home in on this one for a second. So the basic idea here, and maybe this data frames thing is as a name for it, is the that what it is. So I'm going to summarize this again, since we seem to have forgotten what it was. I mean, I hope other people remember what we were talking about there. So the way I see it, I mean, there are a few sort of core issues that we're dealing with here. Okay, let's make a list of core issues. Okay, so core issue number one is accessing arrays, framed, templated, whatever. Framed, I don't know what the right word is for this.
Is this quantity array and also like column-based
yeah, exactly.
arrays?
Yes, that's what it is. So this is scaffolded arrays. Okay, which means an array where, i.e., an array where there is raw storage that is different from the externally visible array element addressing, etc. Does that make sense to people?
Yep. Yeah, like it has an interface that quacks in a certain way, but
that is correct. Yeah. I.e., the array has an outside interface different from its internal storage.
I mean, what this maybe, I mean, depending on how this would be done, it kind of sounds like this could just be like either an extension of packed arrays or something like them that allows support for some of this templating stuff, maybe also for missing and stuff like that.
Right. But so implementationally, we would like this to be implementationally, we want a single interface to all of this. So this is kind of like we define what is a scaffolded array. Oh, it supports certain operations.
Right, and we have that with structured array.
My impression, at least from last time, was that structured array is much less structured in the operations it supports, where like each structured array type has its own, or like you can't have like there isn't like a set of here are the 10 functions that a structured array has to implement in order for it to be quote unquote fully supported. Instead, it was like every function you want to support structured array, you have to give it a particular implementation for every structured array type. If that makes sense.
And also, like,
that's I mean, that's not really true. I mean, right, I mean, structured arrays are sort of natively supported in several dozen functions, right? Like, and some of which are quite specific, like
Okay.
inverse.
Let's
But
just
if you right, I mean, if you create a structured array, then all your basic things like part, extract, etc., listability come along for the ride.
Right, but I guess the
So
point
I
is
think
stuff
that
like intersection, for instance, might not come
no,
along
makes
for
no
the ride.
sense. No, it
Yeah.
won't. So if you define, so in all cases, an array is the general case. So it can always be coerced to a general array. Okay, if you define a new data structure that should have different workflows, then that's probably not appropriate. Let's say that you want column-oriented storage where you think of the column variables as something, like for data frame, or you want missing data supported. Missing data has nothing to do with arrays.
I don't understand what you're talking about. I mean, what we're talking about here.
So, but what is the purpose of this meeting? Is it?
We're going over what
we're
going to do, and let me describe this thing. What we need is a wrapper that, for example, for column, we would like to be able to use the same technology for column-oriented arrays as we do for quantity arrays.
I think there's one thing that was on top of the other notebook that we're leaving out here and it's causing some confusion. And it's the fact that we started out thinking about lists of associations and associations of lists, not arrays. So you can consider the array like the number indexed version of this, and
Sure.
you can probably convert it into that. But most of the out of core stuff and so on is going to be more like a data frame, as Roger was saying, than as a structured array, because you might want named columns rather than numbered columns.
I'm sorry. Look. What we're talking about here with the scaffolded arrays concept is, in the end, as it is for machine learning, for example, the thing has been mashed into what is essentially just a regular tensor, right? With essentially numeric indices, right? But that is not the way the user sees it. The user sees it as, oh, I've got these named columns, I've got units for these columns, etc. Am I making sense?
Yes.
Yes. I think that structure arrays are a very particular case of this idea. So there are three things. There are three things that structure array doesn't handle, which are associations, ruggedness, and types. And so, structure arrays are
none of those are arrays, basically.
Okay, who cares? I mean, this is what we're talking about. Okay, hold on. Maybe the name array isn't even in here. Okay, what we're talking about is what are the scaffolding elements? What we called wrappering over here. Okay, one is naming of items with association keys. That's one type of scaffolding, right? Where you say globally for this whole thing with 1 million elements, each thing, there are 3 different named keys, and I'm going to use those, right? But you're not repeating those named keys because the inner object is just the raw array. Does that make sense to people?
Yeah.
Yes?
Yeah.
Okay.
Yeah.
Another thing is units.
Or like types in general.
Well, okay, types are not what we would normally be dealing with, but it might be convenient to have uniform types. You see what I'm saying?
Yeah,
that might be.
You would have uniform units surely down a column, wouldn't you?
Absolutely. The whole point of this. Okay.
So that, in that sense, they're similar.
Okay.
That's
Fundamental principle. You can do scaffolding when there's some uniformity, right? If there's no uniformity, if every element was its own expression with whatever, then you couldn't scaffold it in a useful way. Does that make sense?
I think there's no H in scaffolding. That's why it's complaining.
Yeah.
Thank you.
But of course, it could be the scaffold where you go up to meet your end.
Well, I don't know whether, I think all of these are scaffolding. Sure. Okay. In any case.
Well, one limitation with units is are strings something that we want to support here?
Yeah, I bet they are. Okay, so there's a question mark about strings.
I mean, but presumably though, the idea is not that we necessarily have a fixed list of, like, it seems like, okay, like, it seems like strings and missing are probably more issues for packed array or something like it. And that this other stuff is kind of different, right? Because the point being that, for example, missing, the question is, what kind of list do we consider uniform? And right now the answer is, it's got to be uniform list of integers, uniform list of, reals, complexes, whatever, and if there's a single missing in there, it's not uniform anymore. So it seems like the issue there is just with strings and missing, it's just that we want to be able to consider those uniform.
Right. Yes, exactly.
But that's kind of an implementation detail. You could use some non-element which matches the type, but is actually replaced.
Right,
by
right. But the whole point is, goal is make the array quotes uniform with a, let's call it a NaN style call out.
Yeah.
Right? In other words, let's imagine, go ahead. Let's imagine that every time we have a numeric array and we put nans in it, and then the scaffold says, actually what nan means is missing.
Steven, when we looked into, we started exploring possible backhands for this, especially if we want this to scale to out of core, most of these do support missing and nan separately, natively. So that wouldn't be a problem.
Fine.
So because they're not designed for linear algebra, they're designed for data science. So
exactly, that's what I'm saying. The workflow is a little bit different than linear algebra. They're related, but they're not the same. So there's no such thing as missing in linear algebra. It makes no sense even. But for data science, it's key.
Okay.
It's
absolutely key.
Okay. Fine.
Another important thing, I did some testing last week and about storing columns with structured arrays. Like you have a quantity array to store a column of temperatures, and then a numeric array to store a column of vectors. And one thing that was very slow was extraction. Like when you take out a row and you have to extract a number from the quantity array and you wrap it into quantity, that's super slow. So
that's some implementation issue. I don't know what that is. I can't comment on that.
Well, but it's maybe important because for stuff, maybe it's important for whatever interface there is for this, though, because, for example, if you wanted to map over one of these things, like if you want to map over a quantity array, and every time it calls the mapping function, it has to turn it into a quantity.
Right.
Then that's
right.
Yeah.
So
exactly.
there's sort of transducer style programming, which means, at least my interpretation of that, which means, when you say map F onto a scaffolded array, that the whole idea is that somehow you not have to unpack the scaffold. You'd be able to do that. You see what I'm saying? That the thing, is this making any sense?
Well, I think at some level, though, the F, if you want to be really general, the F does kind of need to see a whole quantity object.
No, I agree. But that means, like, the F sees a quantity object, but it is assembled, a quantity object, but it is assembled, it's like, it's assembled for it as a fake world, so to speak. On demand.
Example, actually, Stephen, in this demo that I have today for streaming, I have such things.
Okay, interesting.
This is also a problem that we had to solve for databases, because most database backends support date operations natively, and SQLite doesn't. So we actually store and compute things with Unix times. And it's completely
okay. I get it.
Like this. So it can be done.
By the way, presumably dates are another thing then to add to the list of missing and strings. Although I guess dates are really the same thing as quantities.
And categories, categorical stuff. If we think data science, if we think that this is a big container for that, then categorical stuff, date stuff, just go down the list of what's there, and it has precious little to do with linear algebra.
Roger, can you give me an example of categorical for concreteness?
Finite enumerations,
Finite
so when
enumerations.
people fill in a form, you're going to pick from 5 different things, let's say.
Days of the week.
Okay.
Yeah, days of the week, or colors, or we are
not quite colors, genders maybe.
Yeah, genders is a good example.
Complicated.
And some of them are not just nominal, but some of them are ordinal. So, like good, better, best.
Mm-hmm.
But if you look at what the kind of data that you need to process, it's full of those kinds of values. Because in many.
Sorry, I've spaced out for a second. You're talking about categorical data.
Yeah.
Right. So that's another good example of another D-transduction, or something. What is the right word? What is the word for the inner version? Another.
Well, they're both transducers.
No, I understand.
Both a microphone and a speaker is a transducer.
Yes, I know, Roger. So what's the thing that is the raw, another, raw to cooked transition?
Right.
Is it covariant?
Well, yes, it's covariant, contravariant, something like that. Another raw to cooked transition would be for categorical data, where you store it as 1, 2, 3.
Yes.
Right.
Maybe another thing we should talk about is degradation. Like, if you're doing everything in memory native Wolfram language, you can do anything under the sun. But as soon as you're starting to process stuff that is bigger and that is maybe out of core, then maybe not all functions.
No, but yeah. Okay, I understand. But you mean the data is degraded or the functions are not available?
No, the functionality, like how do we communicate? Listen, you can't really do this on a terabyte sized data because you're processing it on a server, not here, and the server doesn't know Mathematica.
No.
I mean, in some cases, there is stuff like, there is a lot that we can do with the compiler. Like if it's sitting on your machine and it's running, say, on SQLite, you can use a compiled function. You can link to external functions into a callback into the kernel itself. That should work. So if it is compilable, then it might work, but not everything is compilable yet.
Sorry, say that again. Sorry, I
said that
you're saying
if you're running something on your machine, like there are databases, but out of core, there are databases that have external function interfaces. So if a function is compilable with the new compiler, then you might be able to run it out of core, even in parallel, very efficiently.
Yes.
It seems like at some level, I mean, can't it just fail, right? I mean, like in the same way that, if you have a quantity array and I don't think you can map over a quantity array. If you try and call map on a quantity array, it probably gives you a message and fails. I mean, is there any reason you can't?
You can map over a quantity array. I mean,
okay, well,
there's some operation. Might normalize, and
you can't do select on a quantity array though.
Probably
you should
not.
be able to.
Right, there's some operations. It doesn't matter what the operation is, but there's probably some operations like that.
Right, you can't select over a quantity array or a sparse array because those are more general than a flat list, which is what select expects. Which is why we didn't implement that. Also something like normal, right? If you take a sparse array, or a very large symmetrized array, right? That's the symmetrized array. If it's totally anti-symmetric, can represent with one element, n factorial non-zero elements or n to the n element array. You can normalize it up to a certain point, but after a certain point, it just says, well, not enough memory in the universe to normalize this symmetrized array.
Can I say a quick point? Stephen, you wrote, uniformity of type CF packed arrays.
Yes.
that's a great assistance to making compiled code, because if you know what the types are, it's very helpful for making efficient compilable code. I mean, I'm sure you know that, but I'm just stating
I'm well aware. Right.
Yeah.
Okay. So I just want to bucket the things we're talking about here. Okay. We also talked about, well, we're about to see the demo from Leonid of lazy stuff, which is going to be the beginning of this discussion of general out-of-core operations. And what we had discussed last time is that what we think we should have done, or still do, is this approach. Okay. What we did do was we have our own special sorted entity class, et cetera, functions, rather than having the ordinary functions operate specially on, indirect out-of-core objects.
Stephen, if I may, I would like to point out that perhaps after this demo that I make, I might say a few words in favor of the approach that was taken for databases, even though for streaming, I take exactly the approach that you mean as the first one.
Yeah, I don't think it's the right thing, but, okay. And then I just want to, again, in terms of what we're talking about here, we talked about these different sources, data sources here. And we're also, the other topic that we're not covering in this meeting, but we need to cover in a different meeting, is generalized disability and the whole inserting business and so on, right? Which we're keen to get implemented. We need another meeting for that, right? We had not, or have we solved the design for that?
I don't think it's finished.
No, we haven't solved that. I mean, it's a difficult thing to implement in the kernel because it requires touching the evaluator. So we are kind of scared of going in this direction. But
okay, well, we'll need to do
it.
So, yeah, we need to do it. I mean, this is something we need to do. So, okay, should we see Leonid's demo?
I'm ready to share whenever you are.
Go for it.
Okay. Okay, so I will try to be brief, and I made this demo in such a way
that is such a suspicious statement, Leonid.
Yes,
I know. You stop me whenever you feel I'm not.
Okay, I love Leonid's. I will try to be brief, and we see there are 33 slides. Okay.
Oh no! Out of these 33 slides, only maybe 15 are relevant, and out of those,
all right, okay,
only 5 are really essential.
Okay, all right.
So, should we start with examples, or should I briefly outline the design goals and main ingredients?
Let's just see the design goals, but maybe not talk through them in great detail.
So basically, it's supporting lazy computations.
Okay, we get it. Okay, we got it.
Keep going.
Okay, good. So the ingredients are basically a list-like object called lazy list, which supports a limited subset of list API. Okay. And then some ideas that are around it, like chunking.
Have you implemented those?
Yes, sure.
Okay.
And I can, if you want, I can show you. I have a slide.
Data sources. Data sources, please.
Data sources are files, potential data sources, because with files, I'm not going to talk much about files today, but the design assumes that all of them are possible. This is what I mean.
Okay, but so the give me a next element is one thing, or potentially, I mean, you're mostly a give me a next element type operation. Is that right?
Not only, because I made an effort to support random access.
Okay,
whenever possible.
Okay, all right.
Yeah. Okay. So let me start with 3 examples. Each of these examples illustrate things which are hard or impossible to do well in the kernel currently, and which streaming does. So first of all, let's start with an infinite list of primes. So here I'm creating an infinite list of integers.
Okay.
Now I'm doing select on that, and notice that it returns a lazy list, but it doesn't do any work yet. So it's now
conceptually okay. Listen, yeah. I as a user don't care whether it did any work. I mean, the blob that comes back for lazy list should indicate that it's different from the previous one. I mean, the ID numbers are different, but that isn't really good enough for me.
Yeah, I agree.
Okay, but I mean, it could be almost like the cryptography system where all you see is a kind of a QR code and colors that just shows you it's different. It doesn't really matter because you're probably not going to be able to show what it really did.
Well, but Steven, this is UX in the end. Yeah, we can.
Yeah, I know it's UX.
I agree, and also I have to say I basically cut through to internals here because, well, but anyway, I agree with your remark.
Okay.
And so the next thing we do, we take a first million of these primes by applying take.
I get it. Yeah.
And now if you look at how it looks right now, it looks just an opaque object.
Oh, okay, but that's not going to cut it because if I save that in a file, I'm toast.
Well, the problem with this is that you anyway wouldn't be able to keep all the infinite content of that.
No, but that's the wrong thing to keep. I mean, what you should keep is the journal, effectively, of what you did to get to that point.
I mean, presumably that, like, if that's a memory address or something, presumably whatever structure is at the end of that memory address also is not an infinite list of primes. So presumably
yes.
Storable. But
so actually, I have a slide where I show how to store this on disk and load it back. We can easily move some of the structures inside lazy list, so it's going to be easier to do. But
why don't you just store a function? Why don't you just store literally take of select of lazy range? You know, just compose the function that you did there. And
yeah,
just store it.
It might make sense. Right now, it's not completely lazy because it pushes certain things to chunks immediately. So what you are describing, it might be a better solution is to
buffering in it is what you're saying.
Say again?
It's buffering some of the data.
No, it's not really buffering, but it's basically instructs. Well, I can come to that, but basically what's happening is that internally, this lazy list contains of chunks. Not
Aren't
even
the chunks buffers though.
The chunks of data, they can be anything, but they have to be lists. And so the thing is, not all of the chunks necessarily are even realized as yet. So some of them might even be, we may be waiting for, they might not have been realized at all. So it's not required at this point. But what Steven is saying is that we might be even more lazy than I was here and basically not do anything at this point at all and just store everything, all this chain of operations in here, which might make sense indeed. Because what's happening right now is that certain work is done, but very minimal. I'm kind of pushing this work on the chunks so that they know how to behave. But I agree with Steven's comment here.
Yes, but you cannot really avoid being a need to recreate a description of the object after it has run for a while, right? If you want to serialize it. So yes. What I've done in my iterator thing, which we can probably talk about next, is to have a way of a method that returns a held constructor, which when evaluated will recreate the whole thing. And it will have all these select and take and everything still in there.
Mm-hmm. Oh, yeah. I mean, this might be suboptimal, but maybe let me move on because I think conceptually, changing this is not going to be hard. Let me put it this way. Okay.
I'm just curious, what's hiding behind the plus sign?
What's hiding behind the plus sign? Yes. So there are two objects here. I might want to increase the magnification.
No. The magnification is fine. Leave the magnification.
Okay, good. So one object is what is called random access list, and it's kind of a generalization of a list of chunks. And it's a generalization because not all the chunks are required to be realized in the flash at the time when we look at it. So for instance, if I take, oops, I'm sorry. Let me see if I can, did I just, oh, sorry, it seems like I just closed Mathematica, which has been unfortunate, but okay. Okay, so let me go.
Go back to where you were. Go back to that example. Go back to that example.
It was a previous, yeah.
Oh, it was a previous one. Okay. So.
Okay, go back to your construction for a second. We were still talking about that.
Yeah.
Okay. Enable.
I just need to do a few things here. I hope it will work. Yes.
You were describing the chunking, the random access inside.
Yes.
I'm not sure we need to know about that right yet.
Maybe
not. Let's keep going.
Yeah. Okay, fine. I can return to that later whenever.
Okay.
So here, this example was basically showing the timing is a little bit off because it was due to caching, but the main.
Okay, we get it. We get it. You can get it back from its symbolic form, and it's much faster than doing it. Yeah, I get it.
Okay, good. Yeah. Then there is some random access example. I'm not going to show it, but it basically tells you that you still maintain.
Okay, now wait a second. When you say total of first mill primes, right? Why does that come back from the indirect representation? How does it know to auto-normalize that?
Yes.
If you understand what I'm saying.
Okay, so here, let me go to slightly.
Isn't it because that's a vector to scalar operation?
Yeah, so basically, here is the classification of things. And we have to make a decision which of them to make lazy and which of them to make eager. The relevant one to us is that the things generally can be classified as terminal and non-terminal.
Okay, I get it. Okay. I get it. We get it.
Okay,
we're quick, you know.
Okay, great.
I'm sure everybody else gets this too.
Absolutely.
If it doesn't return a lazy list, then it's
yes,
already.
So the design decision that I made so far, and similar one was done for data set, but in a slightly different manner, was that anything that is not a lazy list is basically eager. And
yeah, I got it.
Great.
I mean, it would be good if that was consistently done in dataset as well. I don't know if it has been.
I think it has been, but
okay, all right, okay, fine.
But also some of the operations which are returning lazy list are still so far implemented eagerly, not lazily. For example, sorting.
Yeah, I get it because it doesn't seem to help. But conceptually, we should probably have sort. You know, I have no idea whether a partially sorted list, for example, could be additionally sorted in a chunked fashion or something.
Well, it's done still via chunking, but making it lazy is kind of hard because it's a very non-local operation.
Listen to what I'm saying. If it's a partially sorted list, it is not obvious that it's so non-local.
Oh, yes, maybe. Okay, but that's a more special case.
I know it is. I know. The general case, obviously, sorting is non-local.
All right. So let me go to the next example, okay?
Well, let's see the random access example. What's the random access thing?
It basically shows that no matter where you take your elements, you can maintain similarly. Well, the actual.
No, but if you go back to lazy list, go back to your lazy list thing at the beginning there. Okay.
Right.
Go back to your select integers, comma primes. Okay, the primes thing. Okay, now I want to see primes, the 10 millionth element of primes. You know, take part 10 million of primes.
Okay. Oh, okay.
No. Well,
take
primes. No. Primes. Opened double brackets. 10 million. 10 to the 7. No, 10. Oh, whatever you want to do.
10 million.
Yes.
Like this.
Good. Yes, like that. Close the brackets.
It'll take a while, but okay.
Okay, well, let's see it. So what's it doing right now? It's going through the chunked list. It's got a generator and it's going through the chunked list.
Yes, it's going through the chunks to actually get you the 10 millionth prime. And
no, it's not the 10 millionth prime, is it? Oh, it is. Yes,
yes, because you requested this.
Yeah, because it's been compressed down to primes. Yep.
Yes, but what also happens is that as it goes through the chunks, their sizes get cached. So next time we want to use the chunks, as soon as you know which positions you want, you don't necessarily have to go through the entire process once again. And this is this meaning of random access that I mean, that it's kind of amortized random access. Certain things like select, you can't have random access immediately because you don't know how many elements you'll have.
Yeah.
But if you build on that select, and if you have run it at least once, then it caches the size of chunks.
I get it. We get it. We
Okay.
get it. So by the way, I mean, obviously in this case, okay, you might have
it's a little bit more. It's a little bit too much.
Okay, all right, kill it.
Okay, fine. If you want the millions one, probably faster.
Let's do the 100,000th one, just to prove to me that it works.
Okay. It was fast because it was already cached.
Cached, right.
So it doesn't throw away anything. So it's not.
No, it does.
It
only caches.
Right?
All Leonid is keeping is the marker of where the nth part actually lands.
Okay.
Exactly, for the chunks, not for individual elements.
Right.
So that I can always locate elements very quickly once I went through it at least once. And this even works if you build something on top of these primes for, like chain, more operations, etc.
Like a select, another select.
Yes, like another
primes
select.
that are, okay. So I mean, prove that to me just for a second. So take primes and say select on primes, selected primes, mod of hash, comma 3 equals 1. No. Hash, comma 3. The prime is equal to 1 mod 3.
Like this.
Yes, like that. Exactly.
Well, that's not a lazy list, but you probably want it's again infinite. So you
no, I know. That's exactly what I wanted. It's exactly what I wanted. Now I want the 100,000th one of those. Take percent sub 100,000. No,
okay.
No. Just percent.
Oops.
Why?
Let's try again. It shouldn't work like that. Let's see. Well, what if I just do? It should have worked. I mean, I was trying similar things before, and it was, of course, working fine. So
in principle, by the way, I mean, this new lazy list, it's using
works.
the same cache as the previous one. Like it's refers to the previous one.
Yes, it refers to the previous one in a more kind of. So this is.
Leonid, what on earth was the difference between those two things?
Can't tell you immediately, Steven. I am puzzled.
Okay, all right, fine.
But it in this way it works. So I have to see.
Fine. I get it. It's beautiful. Okay, let's keep going.
Okay, so so now let me go through the next example, which is a large numerical array.
Okay.
Here, I'm creating a lazy list out of a function, which basically generates me the chunks. Each chunk is a million element, and I'm reproducing 200 million elements in this way.
Okay, I don't understand that function. What on earth is that?
Well, basically, this is this. Initial function gives you the content of a chunk given the index. This function actually, so you pass the index, it's like a carried function. So basically, if I do,
it's like table, basically. This thing you're running is basically table.
But why is it function of a million? Why is the second argument function of a million? Why isn't it just a million?
Well, I had to hold it somehow, and potentially it could have been, some arguments. In the future we might want to make it actually taking some arguments. So I'm using this inner function as basically, a thunk, something which just holds data. I could just as well use hold here.
I think he's talking about the next argument, the function of 1 million.
Yeah.
Oh, this thing. This is a size function, because basically whenever you are creating the lazy list out of the function generator, you don't know exactly in advance.
I know, but why is it in a function? Why isn't it just the number of million?
Because the chunks need not all be the same size, right?
Yes.
So,
yes. Chunks don't
so
need
the
to
chunk
be the same.
ID is coming in as a chunk serial number is coming in as an argument to that.
Yes, and basically this function here, in more general cases, it will be something more complicated.
Okay.
It will take an index, but in this case, because it's a constant thing, I'm just making the shortcut. So basically, but here's the thing. Now I'm taking out of this effectively infinite list built of large chunks, I'm taking 200 million elements.
Yep.
And if I'm trying to make normal, it will complain.
Obviously it won't. Yeah. Okay. But we understand.
Because I have a limit. I have a limit which you can't actually, you can expand, but
yeah, I get it. Let me just read lazy list create for a second here.
Yeah.
So what is that doing? So that's given the index number, it is giving you a function that returns the elements in that chunk.
Yes. So it's
chunked create. It's a chunked version of table.
Yes, it's a chunked version of table, exactly. So it's just one way to create a lazy list, but here I'm using it. There are other ways, but here I'm using this way out of the function, using function. And so if we perform operations, what happens is that you can do total, and obviously because it's we are pretending it's too large to fit in memory. It's like about 2 gigabytes of RAM, but let's present it.
Okay. Yes.
And then when if you compile, if you compile to MVM, it's like still 5 times slower than what this streaming gives you. You can of course compile to C, but still. And here, what this shows is that if I use some counts by, for instance, on this large array of something similar to what you suggested previously, then lazy list takes only 16 megabytes of RAM and takes about 3 minutes, while in-memory computation is about 15% slower, and it's 100 times more memory hungry.
Yeah. Okay. So hold on a second. So you're saying that this lazy counts by, so those operations are, how does this actually work? I mean, it's going through the kernel.
It's up values which are directing these things into streaming special implementations.
How many functions have you done that
implemented.
For? How many functions have you done that for?
I can tell you exactly because I have a list of supported API. And so these are things which are supported eagerly, including counts. And these are things which are supported lazily. Well, streaming map is something special.
Yeah, okay, all right, okay, I get it. So it's a small number of these functions are supported lazily.
Yes.
Okay.
Yes.
So in general, one could imagine the compiler, in addition to its type analysis, being able to tell you for this arbitrary function, which functions in this thing are supported, have a, I don't know. I mean, in other words, we could use the same type of analysis to figure out, because obviously you should be able to get an arbitrary function implemented, but it's just going to have a callback from each chunk.
Yes. The problem really is, in terms of efficiency at least, that you have to be able to factorize the computation well enough into something that can be done in individual chunk.
I know. So there's things that are operations, right? I get it, right? But that's the point. You can, if the thing has to do a sort, for example, where it's taking everything together and it's an infinite list, and you try and sort an infinite list, the thing should just say, I can't do that. And the type analyzer should be able to say that.
Let's try. I think it should complain. Let's try sort primes.
Yeah, okay.
Let's try to live dangerously.
So by the way, just for reference, it's probably relevant for other things as well. How complicated has it been to, to support all of the like the full functionality of those functions? I mean, if you do, I mean, stuff like, maximal by has to support up to and things like that.
Well, it will become complicated. I actually had to stop, but I was hoping that it would, Christopher, one second, I'll just say what happens here. I was hoping that it will complain. It didn't for some reason, because you see there is this finite flag here. Whenever finite flag is false, I used to think that streaming complains, but it didn't do it yet. Here, I don't know why. I have to look at it. Now about your question.
It isn't showing false, it's showing question mark, right?
Yeah, question mark is for primes. For primes, it doesn't know. That's why there's a question mark. For
right,
first million,
you did sort of primes, not sort of integers.
Yeah, so let's try sort of integers.
It doesn't. It didn't get the message from Euclid.
Okay, lazy list is defined for explicitly finite list. The problematic list was, well, the error message might not be ideal,
Okay.
but Stephen, that's
right.
what.
So notice that next thing, as I said on line 31, it didn't get the message from Euclid that they're an infinity of primes.
Yes.
Right, but the point is that analysis of whether that's finite, like if I'd said twin prime there, we have no idea. We don't know whether it's infinite or not.
Yes.
Right. So, yeah.
She probably should have stopped even whenever it's unclear, because here it says that the list is finite. So I'm doing
whatever.
some.
Yeah. Right.
You know,
okay. It doesn't matter. It's a bug of some kind. It doesn't matter.
Yeah, it's a bug of some kind. I agree.
Okay.
So.
But the point that I'm making is that there is an analysis like type analysis, which is essentially a cardinality analysis.
Yes,
that
exactly.
Could be similarly done. I don't know that it's obvious from type theory how one would do that.
I mean, it seems like it might be super undecidable though. I mean, like you just said with the primes one, there's no way it can know that.
Right, but it's like a dependent type theory, right? It's very similar to dependent type theory because it's basically saying the type is integers, but it has this, it has this condition like primes.
Well, but I mean, it just seems like it doesn't matter what crazy type system you have, you're not going to be able to do the select.
No, I know, but in many cases you will be able to do it, and that's the same thing with type theory, right? Okay, let's keep going. I mean, we can't solve the general dependent type problem because it's undecidable, and this is an example of that.
Yes, and to quickly answer the question of Christopher, it's going to be rather hard to support the entire functionality of all those functions, but in many cases, what I'm doing, I'm trying to kind of piggyback on the existing implementations and pushing those to the individual chunks. So the actual implementations of these things sometimes are very simple. So that makes it not really hopeless, but supporting all the range like up to and things like that might be kind of involved.
Okay, onward, yeah.
Onward. Now, okay, this way, okay, this is the first thing we've seen that. Here, I think, yes.
We saw this, we saw it.
We saw this, and we saw that the in-memory version
is magnificently smaller, right?
Yes.
I mean, your lazy chunking thing is magnificently smaller. By the way, I assume that when you exit the session, everything just it's all cleaned up. I mean, this has a bunch of files hanging around. But they all clean up.
They should be. I have to check whether how well this works, but I did some work on that, and they should be cleaned up. And also,
are they in the temp directory? Should they be launched? Should they be created in a temp directory in case?
Yes, they are direct. They are created in some subdirectory of a temp directory.
Okay.
And also, some of the chunks are not file backed even. Like for instance, these infinite primes, because I
get it. Yeah, I get it. You don't need anything big to back it.
Yeah, because they are generated by a function. So although I can optionally instruct that they have to be file backed if that function is expensive.
Okay.
Now this is an implementation of moving average, which shows that you can actually implement things using the framework and kind of getting new things out of it. And it's just kind of making us kind of translating one of the famous mathematical implementations of moving average, where you just shift large arrays and kind of transpose them. And then if you
so lazy list transpose. So most of what you're doing with these lazy lists is one-dimensional, one-level lists, right? You've got an infinite one-level list.
Not
what is lazy list?
Level.
Okay, so you can do two-dimensional chunking in some sense.
Yes, it doesn't really. Yeah, it does work, and let me put it this way: the chunk has to be a list, but the elements of that list can be anything. That they can be lists themselves.
Okay, but so wait a minute. So you are only chunking with respect to the top level of the nested list array.
Yeah, that's true.
Is that correct?
Yes.
Okay.
Yes.
So lazy list transpose, is that a cheap operation or is that a horrendously expensive operation? It's got to inspect every chunk.
That's a cheap operation because it doesn't do anything in advance. It basically.
Oh, I see. It's just array. It's just an array gymnastics thing.
Yes. And then that's exactly what I'm illustrating here. So I'm having here the lazy list of 10 million elements.
By the way, I just want to comment on something. That kind of array gymnastics stuff, when we were talking previously about scaffolded arrays, that's another thing one could imagine doing with them. It's some kind of transposition, it's some kind of basically trivial transposition.
Yeah, here it's a little more complex because you have to take chunking into account, but otherwise, yes.
Okay.
Well, actually, it's pretty complicated with the scaffolded arrays too, because I mean, for example, with quantity array, when you take the transpose, it's pretty easy. But if you have, if the same framework is also used for the column-based association, or column-based arrays, basically, then a transpose is like an association transpose, which is a very different operation.
Yes, that is correct. Right.
Yeah.
Because of the fact that the associations are uniqueified. Right.
And actually,
that's the reason, right, Christopher? That's
well, no, I mean, it's just that the reason. I think it's just that it's because the scaffolded in quantity array, the scaffolding wraps around a single element, right, as opposed to having one sort of piece of scaffolding wrapping several elements.
Mm-hmm.
I don't agree with that. I mean, if we're storing right, if we have an association of lists and we're saying, oh, secretly this is representing a list of associations, well, then the transpose operation is no, this is now truly, right, that's just a flag saying no, this is now truly an association of lists rather than secretly a list of associations.
So that one will be okay. That one, there's no equivalency worry. All right. Anyway, sorry, that was off topic. Let's keep going.
One tangential comment I have for this is that since lazy list doesn't largely care what are the chunks, those chunks could as well be the sufficient tabular data structures as soon as we have them, and it will be very easy to accommodate inside streaming.
Okay. Can the chunk be itself a lazy list?
In principle, yes, and I think I had some examples, but not here, where it was the case. But in general, it's becoming hard if you kind of nest, if you nest the laziness, because you have to, since lazy list doesn't support all the operations of the individual chunk, you have then to be careful what that thing is.
Okay.
So let me show what this thing, what the point of this example is. So here is a reasonably concise implementation, and then I'm asking for the moving average with the window of 5. And what this shows, hopefully, is that even though it's 10 million elements, because of the way a lazy transpose works, you don't have to compute the full lazy moving average to compute the parts that you're interested in, like 10,000 elements from the start.
I get it.
And if you look at the max memory use here for the entire thing, now I'm making normal, so it's basically all converted to normal. Then it's like 8 seconds, and it's about 100 megabytes. Here it used to be 50. I don't know why it raised to twice. But the point is, for the moving average in the kernel for the same thing, it's like 4 times slower and 8 times more memory than the streaming implementation.
Okay, that's nice.
So here we are already beating the kernel both in runtime and in memory.
Mm-hmm.
Now, where to go from here? Okay, so.
By the way, for the kernel, one reason you're beating it in runtime is because the kernel computed everything and then threw away most of it, whereas you're only computing the part you need. Correct?
No, Stephen. I beat the kernel on the entire computation, and that's. Let me show again. The partial computations are here. Mm-hmm. Here I'm doing normal of the entire thing.
Why did you win against the kernel on the entire thing?
I think because of the memory allocation and because of the algorithms that kernel uses internally.
Okay, that's interesting.
But that's my guess.
Okay, all right, okay, fine.
Now, I just wanted to explain a few additional things if you think that there is still time. Basically, I wanted to briefly go through the typical streaming workflow that you have to obviously construct it somehow from external data.
Yes, let's see it. Open it. Open.
Well, it doesn't have any examples. It just has some.
Yes, I understand that, but go ahead, right?
Okay, now the other few things I want to very briefly touch would be
well, can we look more at construction? Do you in fact have examples of construction? Do you have a design for how the construction would work?
Yes. In general, there are 3 ways I'm supporting right now. Either it's explicit data where you just have the data in the kernel, and then you just say, okay, what size of chunk you have. If you don't say, I think there is some defaults on chunk size.
Okay, now, so that's just saying, I want to chunk this now, but I already had the whole thing, as opposed to a generator.
Yes, that's right. It's a relatively, I mean, the number of cases where you would really need this is probably not very big, because if you already have something
I guess it. If you already have it, then you already have it.
Yeah. Then the most important thing, I think, is to construct it from the object which I call list iterator, and where I think my work overlaps with the work of Roman and maybe other people in the company, because I have internally kind of interface defined inside streaming, which is called list iterator. And so basically any source that is implementing this list iterator can be consumed by streaming. In this case, I'm having this make data list iterator out of explicit data, but there are other iterators which can be built out of other things. And I have actually an example of such. Let me quickly jump to that.
But fundamentally, the idea of an iterator is it's a give me the next element type thing. Is that right?
Yes, except in here, I'm extending it to say, give me next chunk of elements.
Okay, fine.
Just for speed. Let me see if I should have it somewhere. Yes.
And Roman, how does this relate to what you've built?
Well, the main difference to my iterators is that my iterators are mutable, and so they consume. You cannot go back, right? It's strictly for accessing elements one at a time, which of course then extends to functions like select, where you might have to access more than one element until you find the next result and so on. So mine is strictly about iterators, which are most useful probably for combinatorial generators. Like give me all the binary trees, but not all at the same time, but give me the next binary tree. Then many of our operations work just as well, one element at a time, than if you generate all the elements first.
Right. I mean, sometimes not trivial. Some algorithms do not, like binary trees. There might be a recursive algorithm for generating that does not make it easy to go one at a time.
Yeah, I mean, there's that. I mean, for binary trees, the problem is solved. You just look in Knuth, the art of computer programming, and he has lots of algorithms.
I'm aware. I know.
So this particular case, yes, it's rather efficient to generate the binary trees one by one if you compile the result, if you compile the algorithm, right? And of course.
No, but I'm saying there are plenty of cases where it is not the case. There is no trivial transformation from a recursive program that generates a complete collection of things to a program that generates them one at a time. That is not a trivial transformation.
If there isn't one, then you cannot use that paradigm.
Okay, fine. Yeah, right. Okay, but so it's a give me the next element, or give me a certain numbered element, perhaps. Is it give me the next element, or is it give me the element number?
Well, at the lowest level, it's very basic. It just requires you to have a function that returns the next element. Now, of course, higher up, you can easily extend that. Give me the next. Give me.
Yeah, okay.
Next case element, and there are two cases. If you do nothing, it will just use the trivial implementation. Just
but for combinatorics,
it 5 times, right?
Super common. Like combinatoric is full of these. We call them ranking functions.
Mm-hmm.
Okay.
Yeah.
And
that's an area where it's rather well developed.
And if one iterator does have a more efficient way of generating the 5th element without the other 4, it can always overload that generic implementation, and then it will become as efficient as possible. I mean, like, for example, a good example is map. The output lazy list is the same size as the input, so it's quite easy. If the input supports look ahead, then the output does as well. But if you do a select, then you lose that, and there's no way to jump ahead without computing everything in between.
Mm-hmm. Yeah, that's true.
Okay, let's see this.
Okay, so what this is, it basically creates an iterator for lazy list, which reads a file one string at a time. So unit of work here is a string. So this is an implementation. It basically is have an interface that one has to implement. Basically, one has to implement 4 functions: initialization, next element, closing, and asking whether it's still active, and closing.
Surely, by the way, design-wise, those should be in an association.
Yeah, absolutely. This was done before. I think this was done probably before associations became a thing, or at least or shortly after.
A while ago. Okay, all right.
Yeah, but yeah, surely. And then there is another thing called writer, which is another interface where you have to basically implement opening the write, then the writing next chunks.
Yeah,
okay.
Get it.
Then the next thing you do, you register this writer and reader, and then here I'm importing the US Constitution text, and now there is this lazy list import, which is a function for lazy list, but it could conceivably be integrated with the import at some point. But so this is the name of this format that we have defined, and here we go. We have a lazy list out of this new format, and now you can basically access it element-wise, or you can export it.
Okay, so the fundamental point here is, just like in import, you can ask for this element or that element. You can ask for a data set. You can ask for this or that. What you're saying is, imagine a case where you could ask for a lazy list.
Yeah.
Even though, in that case, one feature of import is, after you've imported something, you could throw away the file and it's still good. What you imported is still good. In this case, there's still an umbilical cord, so to speak, connecting the imported thing to the original source.
Not always. It depends on how you do it. You can do it eagerly and create a lazy list so that it will be read entirely, or you can keep a kind of...
I get it. So one case is that it streams everything through your framework and then delivers you a separate immutable copy, so to speak.
Exactly.
Okay. All right. So that case will be the case that will be natural for import.
There's if you think of media, audio and video, so let's say that you stream things. Initially we did things where you download the whole thing locally. So it doesn't go into memory, but it's still local. And then the other case is that you don't do that. You want to be able to show it kind of right away as soon as you've buffered enough, type thing.
Right. So this is basically a streaming import versus versus ordinary import with a lazy list element.
Exactly. And actually streaming supports both. I just didn't have an example for the one which will be kind of lazy in terms of importing, but it is inside.
Yeah. Okay.
So for streaming, you sometimes don't know the end of it. So for instance, let's say it's a sensor that keeps reporting new data.
Yes.
Or it's true for video too. We don't sometimes know the end of it. It could be live, for instance, but even when it's not live, you can't always query the length of it.
Yes, it's still supported, which is why in the lazy list, when I have this in internals, there is this random access list here of chunks. This thing generalizes normal list to the case where not all chunks have been already materialized. So it allows you to add chunks as they appear in principle.
So could this be hooked up to a sensor that keeps
I guess it could, although it would be sort of interesting to see how to make things sort of non-blocking when the new data arrive. How would you can of course request all the time and it will show you, but it's probably
it's the wrong model. Probably it's the wrong model.
I think it's the wrong model because I think it's going to get the blocking thing. The concept that something from outside the process can block you seems inconvenient for this.
Yes, I agree.
But also, if you think of a sensor that runs forever, the fact that you think that you're going to tally it up in a long list seems like wrong.
Yeah. Okay. Onward.
Okay. So perhaps the well, there is something I wanted to very briefly show is that you can basically persist. I have this lazy list put, which allows you to persist disks on persist lazy list on disk, and then lazy list get to get it back. so that this way you can serialize things for be available for the new sessions. I didn't really want to put too many.
I mean, there's more to design around that. I don't think that's
Absolutely.
necessarily the right way to do it. I mean, well, maybe functionality-wise, this may be fine, but I don't think that's how it should be presented to the user.
Probably, I'm sure. It was more just to say that this aspect is kind of has been considered, but I'm not saying the design is perfect. And the last thing I wanted to show very quickly is the
you know, Leonid, I do love the way that you put the phrase very quickly. Never mind, keep going. I'm just giving a hard time.
Okay.
33 slides tells you something.
Okay, yes, so let's try to do this in 1 minute. Okay, this slide, and this will be the last.
Okay.
I just wanted to show that it's pretty easy to extend the framework. Let's say the standard deviation is not yet in the framework, which is true. And well, it's obviously the obvious formula how you compute this. And now what you do is that you make an implementation like here, which is the streaming implementation. Then you can basically test things. And again, I can as well run it, but the thing is, it's going to be basically much more memory efficient than the in-memory thing, while slightly slower. But then you can register the implementation like this, and then I can use standard deviation that the system.
I get it. So my question is this: lazy list chunk fold, for example. How many creatures like that are there? How many functions are there?
Just maybe 2 or 3.
I don't believe you. We've already seen at least 10. We've seen all kinds of lazy list create. We've seen all these things.
Yes,
what are the special lazy list functions? Just to question mark
create.
Yeah, just do names.
Just do question mark. Leonid, just type question mark lazy list or lazy star. Lazy star.
Yeah, but not all of them have to be exported to the top level. So the question is, obviously, which ones the user may want to use.
Okay, which ones of these are there that are of that type, which you would seriously use in implementation of a lazy list construct?
Well, I would say probably these 3 and maybe a couple of more, but I think they're definitely below their number is definitely below 10.
Okay.
And even they are actually used here for performance. You could just as well use fold, but in that case, I wouldn't be able to make this thing as fast as this, because this instructs it essentially to do things per chunk and to bypass any kind of.
So one possibility would be a headdress for a bunch of functions.
Absolutely.
Because we have a similar headdress with batch applied, right?
Yes.
What is the relationship between batch applied and chunking?
There is no relationship currently, but
I realize that.
But I'm using internally something similar to batches, so we can see if there.
So let's look at whether because that would be. I mean, in fact, we had a question on the live stream which I've been kind of ignoring here from Ethan about chunking database queries, and that is what batch applied is doing, is it not?
But not in relation to databases, I think, because
okay, it's in relation to the entity framework.
Yes, and for database.
Yeah, go ahead.
Yeah, what I was thinking is, like, with respect to all this stuff with the headdress and special functions, and also to answer about databases, I think that the approach that Tom has been using for data structure is very, very promising, because you can define a number of these low-level functions that only work with a certain data structure within the data structure as well as methods.
Yes.
And then you use those. I mean, the idea would be that.
I get it. So instead of a lazy list chunk fold, you have a lazy list data structure. The thing lazy list is a data structure, right?
That
Tom style data structure.
I mean, that would work unbelievably well. And by the way,
I'm not sure it can be a data structure, an actual data structure, because data structure is documented to have as
It could be something else. It's totally.
But why can't it be a data structure? Why couldn't
data structure has the full data in like the second argument? That can't work for out of core stuff.
Well, data structures have a serialization and a visualization. Yes, that's
right.
That's
so we could redefine that, but the concept of fitting this into data structure seems rather good to me, because then we don't have to have all of this. Then that lazy list chunk fold just becomes a data structure operation, which we need to write better design for, but on this thing, we don't have to have another whole world of. Anyway, that sounds like a good idea to me.
Yeah, and
by the way, I'll just say data structures also have iterators, and writing that mean you just implement the iterator, and then lots of other functions just start working by the way the type system in the compiler works. So you just implement the iterator, and then you can start.
I think this is something Leonid needs to learn about.
Yeah.
It could be a new thing that we start. Maybe it's not data structure, because many people think of linked lists and other things. Yeah, but let's say it's a data model. So it's kind of like a set of interfaces to data.
Yeah.
Kind of like data structure is in a way.
We have a nice internal mechanism for working with these things through the compiler. That's for sure.
I see.
I think
but see, I'm kind of thinking that. Think of this going on for a number of years, and we are going to connect to all kinds of outer core data, data models, basically, and how we distribute operations between things that are run very close to data and very close to, the compute, where you do your main compute. That's going to change over time. Do you know what I'm saying? I could imagine that we have even distributed data models. That's very uncommon now. We are happy to have one outer core sort of data source, but let's say that we have several of them. It's not relevant right now, but it might be in 5 years.
But there's one thing that we were talking about with last time. I think Christopher said it, which is if we have like a smallish interface for all these kind of low-level data structures, and then we have a number like out of core, in core, and whatnot of these data structures, which all have a similar interface, then you can have a higher level construct that consumes this stuff and implements sort using the lower level stuff or intersection and so on. And I think that's a very powerful idea, because then you're kind of abstracting away the single implementation, and it's the job of of the higher level data structure to say, oh, sort is done by this lower level operations.
We have some. Yes, that makes sense. Okay, we have to wrap this meeting in a moment, but we have a few comments from our live stream, which I think might be interesting to look at here. Let's see. Let's see. Is it possible to pass a single copy of the array variable so that it is shared between all available kernels and processors? I'm not talking about set shared variable, but rather shared by default. So there's questions about parallelism here. And I assume that once you're chunking, you could in principle be running different chunks on different processors. Is that a true statement?
Well, the true statement would be that the design of streaming doesn't prevent that.
And Roman, can you comment on how that would relate?
Yeah, but I mean, you would have to send all the data back and forth.
Yeah,
you could do it multi-core. The data might be on different machines. So having
I mean, if you can parallelize the constructor so that each kernel would just create the chunks that it has been assigned to compute.
Right. So that's what I would do all the time with parallel.
Yes.
I mean, it would make a lot of sense. But let's say that multi-core, like run these things in multiple threads. Then you don't have to move data around.
Oh, and by the way, regarding this, I wanted to make a few remarks for compiler that streaming is pretty agnostic to what kind of things it passes to the chunks. So I did experiments. It can pass, for instance, compiled predicates, etc. And one of the directions to speed it up would have been to integrate it with the new compiler and be able to pass computations on chunks to the basically pass compiled functions.
Yeah, sure. No, that absolutely. And
but
you
for
should
parallelism
use data structures,
and
data structures as a source for your chunks
and
as well.
just to mention that something I forgot earlier, that so Leonid, if you could help me, just type parallel map of f comma range 1 million, just so I have something to show. And so this range this does not expand the range on the master kernel. It dissects it symbolically and sends the range commands to the other kernels. So this already does something similar, but it recognizes range as a constructor, and it avoids the.
I had no idea about that, Roman, because I have done this. I have by hand done a version of this many times.
Oh no,
that's pretty old. But one thing is that if each core has separate access to storage, let's say, so it's effectively a parallel storage access, you know, and you're drawing from something that's big, then we should make more functions that can do. I mean, every one of our kernels does have its own I/O system, but I don't think we've made it super easy to do right now. But it's one of these.
Okay, so that's one item here with respect to, you know.
So you're talking about shared file system access? Or?
Yeah, exactly. Shared file system or other shared storage, you know, but they all can sort of separately access it. So it's parallel.
Okay.
Yeah, and I guess the design of streaming currently doesn't prevent any of that. In other words, it wouldn't be hard to generalize to that because nothing there really is fundamentally, you know, preventing this.
Right.
Okay.
We have for an external appointment.
Yeah, I also have to go in a moment. But we had a few comments here. I just wanted to look at them from Ethan here, suggesting use cases. Okay. Data science and high frequency trading, detection of causation between terabytes of time series. Phew. I don't know. I mean, you could want to do many different things there. It's unclear to me what. Okay, so second one. Go ahead.
Yeah, I mean, the main issue is if you have anything, apply a function to data that you don't already have in memory or already read in, avoid reading in everything at the beginning at all cost. And so I think that's exactly what these examples are about.
Okay, well, storing super large image and video data sets with lots of labels for different types for evaluating multiple tasks. So that's an issue of more like the scaffolded arrays where you have these big images, and that's another use for scaffolded arrays, is where you have some big image asset in the background, and what you're doing is essentially array gymnastics, and you only pull in the big image asset when you
We've looked at that. We think it's a pretty rare use case that you have super big images, but what's super common is that you have big image collections.
No, I agree. That's right. Right. Yeah. Where you've got a million image collections, but
exactly.
The backbone of a million labels is nothing. Yep. It's the images that back them that's huge.
That's exactly how, you know, machine learning kind of works in that same thing. But
you have to pay attention, because you might have like the databases that are so huge that even the metadata can blow up your memory.
I know, but let's assume that we're not dealing with that case. Mm-hmm. There's two levels here. You know, there's a factor of 1 million difference between the metadata blowing up your memory and the assets blowing up your memory.
Sure.
You can live in that factor of 1 million easily. Okay, so that is another case we should look at. Another one, the ETL case, working with streaming data from Kafka. Interesting. I don't know whether we've talked about that as a streaming source. Right? I mean, we're using that ourselves now for a bunch of things. But does Leonid, can you, or anybody else here, can you comment on streaming sources like Kafka?
Well, I don't have any experience with Kafka yet, but I would assume that it should be possible to connect also through.
No, but that requires that what we don't have right now is a version of import that is essentially a streaming import that connects to a stream like a Kafka source.
Yes.
right?
And actually,
that's kind of a symbolic import that connects to a stream, which is what we were talking about before with Roger's sensors and so on. I mean, a Kafka stream is like a sensor data stream.
Exactly.
Yeah, I had somewhere, I was looking for some note that we need a streaming import. I can't find it, but it was somewhere noted on.
Right,
on
but we see, but streaming import, what we need is something which simply returns, and it's very similar to what we do in the device framework. It simply returns, and we should look at the device framework. The device framework may already have solved this problem. Right? Remember, the device framework is looking for data that could be buffered, might be unbuffered, but is data from the future, so to speak. So why don't you look at the device framework and see if that can be used for the streaming stuff?
Yeah, that's a good idea.
Okay, and
yeah, just one last thing I wanted to say regarding all this. I think overall, my picture of lazy list and streaming is that whenever you can think of something as a list conceptually, which exists somewhere, not necessarily in memory, then what streaming does, it provides you this list-like abstraction to operate on using familiar functions, while it will do all the work underneath. That's what it does. And in particular, it's kind of orthogonal to what possible content of that list might be. For instance, that might be, chunks of this tabular structures or something else. As long as it is a list, it should be able to operate on it.
Okay, there was another comment from Ethan here. Unsupervised data science clustering on gigabytes of JSON data from a web scraping job. I don't know. That's requires more thought. Let's see. Nick is suggesting more lazy, a symbolic thunk that only unthunks on demand and can be realized as an attribute for any symbol.
Well, that's much more general thing.
How is that different from like hold?
I'm not sure that it is.
The point that if you apply a function, it applies to the inside.
Well, I think what Nick is suggesting here, which is kind of an interesting idea that we've never had before, is just like we can say x colon equals blah, that somehow, I actually don't know how this makes any sense, that somehow the thing that is returned as the value of x is always itself held. That doesn't make it requires more thought. That's not quite right.
One thing I wanted to comment on here is that being always lazy is kind of dangerous, because when you start nesting laziness, you very quickly lose control over which operations are performed when, and on efficiency as well.
Sure. Yeah, Ali is commenting 4D image stacks can also be large. I think 4D image stacks should be, in any streaming lazy thing that can work with backbone plus assets, that should work. All right, this was an interesting demo. I think there's a number of connections that need to be made here, and I guess we have to keep going on. We need to dig into the design of the scaffolded arrays stuff, and that will be both top-level functional design and internal implementation design. And I think we've got these three areas here. Does anybody think that there's any of these? Well, actually, there's a different one, which is essentially asset separated arrays. I don't know if that's really different. E.g., backbone plus images, metadata backbone plus.
Well, there is another category that we were looking at, which is basically it's in core, but it's not your usual Wolfram language memory layout.
Well, like the compiler would do.
A more efficient way.
Like the compiler would do. The compiler is using its own memory layout.
Yeah, pretty much, but it might be an external process, but it's still memory.
Okay. All right. Well, this was useful. Let's keep going. Let's do this again next week, I guess. Since this week we have a lot of stuff towards the end of the week for the 13 preparation. Okay. Anything else anybody wants to add right now? Nope. Okay. Good stuff. Thanks to folks here and thanks to folks on the live stream.